So maybe just with the agenda, we had a bit of discussion how to do it because there was a brainstorming, but this was more for only part of the people. So we will skip this and put this at the end. So the new idea would be we do 2 presentations, maybe about 1 hour, then do a small closing session, some feedback forms and so on. And then we can go for lunch here in the building as yesterday, and then we would do the tour around 1. Let's see exact times, but that's the rough plan for now. And now we start with Niklas Dicke, and maybe the question to the online participants, can you see the screen?
Yes.
And hear us. Okay, then I open the presentation. And hand over to Niklas, please.
Thank you, Thomas. Okay, so I will tell you today about the hibernation concept of the EMSP. This is the agenda of today. I will present shortly 2 concepts which we were considering, and then also show some results from the demonstration and tests on the EMSP. The hibernation mode was developed within MS Opera project. Paula already mentioned this morning. This project was planned for do the optimization of the operation of the HPS2 loop with solar salt. So it started with a salt change, which Paula already presents, and it ends the end of the year, and we are already now in the hibernation mode. Here are the partners listed. So the DLR is a project coordinator. TSK Flexol was involved. Steinmüller is also involved for the retrofit of the steam generating system, and of course the university as a site owner. The motivation behind the hibernation mode was that we had a massive cost increase in electricity because of the war in the Ukraine. So the prices rised 800%, and this leads to massive problems. And as we facing also now periods without project-related test operation, we thought about concepts to decrease the electrical consumption. When we look to the last year, when we had the full year test operation within MS Opera, we consumed 52 megawatt-hour per month, so that's quite a lot. And I listed also here the different consumptions for different operation points. So we have a standby, so everything is drained in the 2 tanks or in the 3 tanks, drainage tank and test system. With different temperatures, you already see a big difference in the consumption. We have here the automatic solar operation, which is something in between. And then we have here the huge part of preheating and electrical antifreeze in the solar field. So we have an impedance heating of the collectors, and if this is running at a set point of 300 degrees, we're using like 2 times the household would use a year. Shortly to the plant design, I will just go quickly through it as Paula already presented. So it's a 3.5 megawatt thermal solar field. And we have here in our thermal energy storage is roughly 72 tons of solar salt. And we will also look a little bit more in detail into this part here as we use that for the salt dilution process. We did some measurements of the chloride content beforehand of the salt dilution, but I will come closer to this when we talk about corrosion later. And now we are facing a period of roughly 1 year where we are in the hibernation mode, and I will show now the concepts. So we evaluated in general 2 concepts, which is the freezing and melting in the storage tanks. And the other concept is the salt dilution concept. We did a risk assessment to see, okay, what are the risks, how likely they will appear, and what would be the severity of this. And yeah, all processes or all risks which are here in the A matrix should be avoided. Let's take a small look into the freezing and melting. We did some yeah, pre-engineering to see what would be the effort, what would be yeah, potential risks. So for the heating, or freezing, let's say the melting of the storage tank is a complicated thing, because the freezing, you just turn off the heating and everything will freeze. But the melting would be difficult, especially as we don't have trace heating yet around the tanks. So this would be need to install. So all the insulation cladding needs to be removed. We need to do electrical installation and the installation of the heating circuit on the outer surface. And this, of course, is rather expensive. We had some quotations of 60 to 80,000 euros per tank. And yeah, when it's then stored for a year, then the air volume in the tanks also should be yeah, conserved with nitrogen in the best case. And then if you start up, the plan is also to preheat the air volume here to have the lowest possible heat temperature gradients. This is also, oh. So let's see. No? Yeah, okay. We also then considered, okay, when we really freeze the whole tanks, do we need to remove some equipment which might be critical? We already saw some frozen pumps in the thesis facility as well as on the EMSP, which could be then melted again without having yeah, breakages of parts of the pump, as well as instrumentation which could bend or share, what you also saw in the thesis facility. So if you have the density change during the fast change, and the instruments are in the solid blocks, they might move and could bend or be damaged. One major concern were the temperature gradients during the melting process, because the tanks also were not foreseen to be melted from the outside. And this is a critical process where we then looked a little bit into detail with a small FEM simulation. There we checked, okay, if we now wrap around the tank here trace heating, but we cannot put heating on the floor of the tank, what stresses would then result here at the welding of the tank, because this is a critical area here where we might see too high stresses. What we found out is that we should not start with installation of trace heating right on the bottom of the tank, because this leads to very high stresses, which would most likely damage the tank or the weld here in the corner. And the solution would be then to start with the installation only 1 meter above the ground and limit the wall temperature also to roughly 300 degrees. And then the stresses are feasible here in this area. Yeah, so the risk was in a rating of B, so it's a feasible concept, but it is extremely costly. And we, of course, have thermal stress to the walls anyhow, because we will have big temperature gradients. Okay, so then let's take a look to the salt dilution concept. Also a very interesting process where we looked in already with the Yara most, which Paula mentioned. And this was also one of the reasons to decide for this concept. So here's a picture where we first produced some steam in the EMSP. As Paula already mentioned, the steam generator here in the front is still in the refurbishment phase. The salt dilution process, there you mix dimming water with salts. you can do it with nitrate salts, but also with chloride salts. And the hygroscopic properties will bind the salt into the crystal structure of this of the mixture, and therefore you can decrease the melting point of the salt. So if we did some measurements here in the laboratory. So we have here the salt, the pure solar salt, which has roughly a 230 degrees melting point. And on this axis, you see the water content in weight percent. And with rather small mass frictions of water, you already achieve much lower freezing temperatures. What we were aiming for in the tank is a clear point of roughly 48 degrees, 48 degrees, which represents 35% of water. And this would more or less exhaust all the possible volume in the storage tanks. So the idea would then that all tanks are filled to the designed maximum level. When the solution then falls below the clear point, so then we are here in this area. So when you are above, everything in the solution would be fluid. There would be no solid particles. If you are here below the curve, then you would see solid fallout. You have the solution at saturation, and therefore there will form some crystals on the ground and on some instruments. We will see later some photos of that. The good thing is that we also, in this solid salt, you have some water in the crystal structure, and this makes it much more easier to melt again, and also decreases then the thermal stress to the infrastructure, because the thermal conductivity of the water salt solution is much higher than of the solid salt itself. Okay, this is the point we want to reach. One question was the vapor pressure. So if you mix like 290 degrees hot salt with cold water, you would expect that you see strong evaporation and high vapor pressure. We have do calculations with a BET model. This is a theoretical model where you can calculate vapor pressure of this kind of solutions. We did it here for solar salt and high tech. And what you see in the different colors is the water content of the solution. The blue one is pure water. I think all of you know the vapor pressure of pure water. And then we decrease the water content. And what you see is that also the vapor pressure decreases a lot. What we also saw is that this theoretical calculations do not fit with the reality. So in reality, the pressures we measured were much lower. This experiment was also done in HPS1 that day, so it's quite long ago with the partner Siemens. They did proof of concept in the laboratory where they mixed 12% water into 200-degree solar salt and then measured here the pressure. Also some temperatures, but here the pressure is from interest. And the maximum pressure they measured was 4 bars. So this would be here, this point, which I marked here. And from the theoretical calculation, it would be roughly 24 bars. So there's a big difference in between. So the model is not really fitting to the reality. Let's come to the topic of corrosion, because it is always a big question mark in the room when we talk about diluted salt solutions. There were different tests which were done also in HPS1, where different samples were tested with the water salt solution of 12% at 120 degrees C for 270 hours, and then another test again with pure salt, also for 700 20 hours, and what comes out was that there was no significant corrosion, which could be seen. But if you have too high chloride content, you see active corrosion on the surface. So there were tests be done with 200 ppm and one with 500 ppm. And in this, somewhere in between, you have the gap where you will see that the oxidation layer on the top will be removed. So if you are right above 200 ppm, the passivation is still okay, and you don't see active corrosion. Another question when we talk about chlorides is what amount of chlorides we are adding to the system when we mix it with the water. We are using dimming water, so there is not really much chloride in it. But of course, if you do this process repetitively, then it might agglomerate over the time. So we are doing continuously evaluation of the chloride content. By now, we couldn't detect any further increase from the situation we had before the test here. I already mentioned no pitting, stress corrosion, cracking were occurred here in the Siemens tests. But there should be also some further tests for longer durations and also at higher temperatures, because when we're talking about 120 degree and 12% of water, we also would not expect high corrosion. So this would be more interesting if we are working with like 300 degrees water salt solution. So this is something we want to investigate further. Pumps and instruments can remain in the tanks, and the pumps can also be used to pump the media. So I will later talk about in the outlook about that. We also did some further corrosion tests in our laboratories. So we made test bench with the steel samples from the EMSP, which we have in the tanks and in the receivers, and put it into a salt water solution for 2,400 hours. Did an evaluation, and there were no corrosion products on the surface or pitting, or the surface was roughened. So there were no signals for corrosion. But what we also found on the surface before cleaning them, so this is the original sample, this is the sample after the exposure to the water salt solution. So there's some salt on the surface. You also see it here. The surface, it's kind of crust on it. And in this crust, there were several elements were found. So also magnesium, silicium, and also calcium. Might be from the impurities you mentioned, Thomas, this morning. And the calcium is most likely a remaining from the Yara moss we had in the facility before. So then this was the background for the decision. We evaluated it and came to the same rating like we saw it on the freezing of the tanks and melting. And as the salt dilution process is from higher scientific interest, and also the costs were really low, we decided to go with this concept. So here we see the application on the EMSP. We have here the P&ID, or the process scheme, which Paula already showed before. So we are now looking here only to the tanks, to the storage tank area. And what we added here is an injection point for water. So we have here a valve, a pump, and a demi water tank. So this installation we did not really need to build up, because we used the condensate system of the steam generating system. So in the end, it was only a connection with a high pressurized hose, and then having here this injection point. So we have here the cold pump. Below there is a cold tank. So the salt comes here through the piping. We have a valve here, a shut-off valve, and then enters here into the mixing area, where we injected here with this steel tube cold water into the flow direction of the salt. We have here a pressure sensor where we measured the pressure here, and of course heat tracing to keep all the salt fluid inside this piping section, that we are always able to measure the pressure. Okay, so I also brought some trends from the process. What I want to show here is injection when we started it in March this year. So it's not long ago that we did the test, and we did it here with 13 bars. So this is the pressure of the salt, which can be done by the cold salt pump. And then we injected some water. We reached mass frictions of water here up to 8% roughly. But we saw that with a mass fraction of 5%, you have a better mixing, the temperature gradients are lower, and what we see on the next slide is you can also avoid solidification. Because what I want to show here is the second process, which we did in April this year, where we have the same application I showed, but on the hot tank. So it's more or less copy and paste, or it can be changed wherever you are active. So you see, we started here at roughly 280 degrees and injected here then the water mass flow. At the beginning, temperatures decreasing until they are reaching here a point where we need to switch over the tanks, because at one point all the tanks need to be mixed. And this was started here. And what you then see is that the circulation inside the hot tank was reduced, because we were filling from the hot tank into the cold tank to empty the tank more. And then we saw that that we saw big gradients in the different temperatures. So we have the black temperature is the top layer, the gray one is the mid layer, and the brown one is the bottom layer. And this is also what we expected somehow to have on the ground area, where you have only salt and no water mixture, because of course the plant was not designed to mix everything perfectly in the tanks. And as the density of the mixture is different, the water tries to go up and will accumulate more on the top layers. So what we see here is the kind of frozen area in the tank. And over time this decreases then, and then the temperatures are almost the same. So now we take a look to the prolonged storage. So the solution shows a little subcooling, and this is a picture of the cold tank from the 12th. So it's from 2 weeks ago. So over time we decrease the temperature also below the clear point to see what happens. And what we see is that the crystallization starts here on some nucleus. So on the walls, here we have the heater, the electrical ones, the thermocouples, which we have in the tanks. You see here the outlet or the inlet to the cold tank, let's say. This crystallization is rather interesting. So I brought some more pictures from it. So you see here the development of the salt crystallization in the tanks over time. And I also plotted here the temperatures. So we started at rather 50 degrees C, and then moved here to something below the clear point, 48, 47. And then we see that the crystallization starts. So the crystals grow further and further until we turned on the heating. So this is a yellow trend here because we don't want to grow more, let's say. And then we turned on the heating, and yeah, in a rather fast process, then everything is molten again. So then I will come to the conclusion and outlook. So we had a target to reduce the energy or electricity consumption. We met this goal, so we came to an electrical consumption of roughly 400 kilowatt hours per day. And this is reduction compared to 2023 of 78% in average. So that's, yeah, that's pretty good for our budget, because within MS Opera we spend 250,000 euros of electricity. The dilution process and especially evaporation, where we are also a little bit scared, let's say, was easily handleable. So we did the dilution process also with only 3 bar. Without having excessive evaporation. And what we also saw is that the measured pressures are much lower than expected from the bed model, which we calculated. So this is something which needs to be further investigated. The mixing in the atmospheric tanks could be challenging, especially if you have a batch operation like we have it now. Or had it now. So you always should have a recirculation inside the tank to really avoid having solid blocks on the bottom of the tank. What we are planning is in September to have a solar recommissioning of the plant. So the idea is also to use diluted salt now as heat transfer fluid and try to boil out the water on a solar basis, not with the electrical heaters, because of course this will cost a lot of electricity. So this is planned for September, and then we are doing some assessment of thermophysical properties. So we want to look a little bit more in detail into heat conductivity, heat capacity, vapor pressures, and what I mentioned in the beginning, the corrosion behavior at higher temperatures. This is also from interest. At the moment, we are working on a follow-up project because, as I mentioned, MS Opera will end of the year. And we have several possible applications for filling drainage procedures, but also for night operation on emergency drainage and freeze recovery. And if there's any interest from partners, please contact me. And that's it from my side. Thank you. Questions?
Very nice pictures.
Yeah.
Looks like out of space. So any questions from the audience? Rita?
Move on to the energy with the source solution is better than without?
You mean the heat capacity of the mixture is higher than of pure salt?
Yeah.
I guess so, because water has a higher capacity. I mean, it's always a question of the mixture, and if you are above 300 degrees, the water might evaporate if you don't have a pressure vessel. But yeah, it's better for the heat conductivity as well, and also for the heat capacity. Yeah.
Other questions? Are there questions from the audience? Maybe I have a question. You mentioned Yara Most or Hightech XL and Solar Salt, and so I know that you did first the Yara most, and then the solar salt, and you show diagrams, and sometimes it was the one or the other. So maybe you can explain a bit the history and what you did with which one. So
Yeah.
That's what I couldn't fully get.
Okay. We started with the Yara most at the beginning of MS Opera. So to change the salt to the solar salt. And then it was only emptied the plant and the salt was recycled within Yara.
Without dilution or with
dilution?
With dilution as well.
Yeah. And then now we did the operation with solar salt for roughly 1.5 years. And to save now the electricity cost, we also diluted the solar salt.
But did you do for Yara salt also the opposite process of getting rid of the water? No, because you pumped out the salt liquid mixture fully from the plant.
Yeah, and then we stored it in IBC containers, and Yara picked them up and bring them to another facility where they then boiled it out and recycled.
So the next project would be about the starting up, or the upcoming activities are about the starting up process and removing the water. That's still not being done yet. So
yeah. So the idea is to demonstrate the solar operation in September, and in the ideal case, we can use only solar energy to remove all the water. But what we also saw, we already heated up one tank because we failed when we tested the first time. And so we need to repeat on the hot tank another time. And there we already did the process starting from 140 degrees and boil out all the water. It was,
And you expect difficulties with doing this with solar, because in a tank you have a large surface and the water can easily evaporate, but in your pipes, the water needs to go all the way through the pipes to the outlets. So
but it will not evaporate here. We will have the pressure of, depends on the operation state, but between, 5 and 10 bars or something. And what we saw is that the water does not evaporate even at 3 bar.
And then it comes back to the tank, it's atmospheric, and then
it can evaporate.
In the tank.
Yeah, that's the idea now.
Any more questions meanwhile? Online, are there some questions online? Can you still hear us? Maybe somebody can quickly say something to be sure that you're still there. I see.
Thank you.
I can hear you, and I currently don't have any questions.
Okay, thanks.
Great.
Thanks again, Niklas.
Good.
Then we will continue with again an online presentation. From Paula again. So I stop sharing the screen. Paula, are you with us?
Yes.
Yes. Nice to see you again.
It's me again to close the session for today. Just give me a second to start.
The last presentation from Paula will be about preventive and corrective maintenance measures in EMSP.
Okay, I guess you are already seeing my screen.
We can see the screen, yes. I move to speak up and that people can hear you better.
Okay. I will try to speak a bit slower this time.
Yeah, a bit slower because the audio quality somehow is not so good. So maybe then easier to understand you. Okay. We can see the screen. I start full mode here. We look forward to your presentation. Yeah.
Okay, very good. Thank you very much, Tom. Okay, so let's start this last presentation about preventive and corrective maintenance that we held in our facility, a remote and salt platform. I will be more or less dividing this presentation into 3 different sections: preventive maintenance, corrective maintenance, and also major issues that we found already during operation and how did we tackle. So starting by preventive maintenance, well, more or less by definition, I think all of you knows. So those are all the actions and tasks that you will be performing during your operational periods or idle mode periods in order to conserve your equipment. In our case, of course, we will focus especially in critical equipment. The solar field is one of it. All the heating equipment are also critical for us. And also, of course, then the molten salt pumps, the valves, etc. I will be focusing more this presentation in what we are doing during idle mode operation. So idle mode here is the period in which we are in between projects waiting for next test companies. This usually happens in this type of pilot power plants. In commercial ones, it's not exactly like this. So we might have still slight difference from what is being implemented in industry. In our case, right now we are still managing this in a kind of informal way. So we have an Excel sheet. This is a screenshot of it, in which we listed all the actions and tasks that the suppliers of the equipment suggests to us to implement in order to conserve this equipment. And also we try to implement what is our experience with this equipment. For example, in specific, the heating elements, the electrical tracing, we see that in the winter season, if we have a rainy season, they are really problematic because sometimes you have problems with your insulation and quite often you have humidity coming inside. So most likely in the winter season or rainy seasons, we will be activating more often these heating elements, and during dry seasons or hot seasons, it's not so needed. In this case, for our facility, this is a topic because in the end, we don't have a turbine and a generator. So we have high, as Nicholas already explained, high electricity costs. So we really try to manage either the operation or the maintain the idle mode periods in a cost-wise manner and try to optimize all the operations that we held at our facility. So, and still on this topic, costs, it's really a topic for our infrastructure, and I believe for all the infrastructures, research infrastructures all over Europe and worldwide. And so this table just presents briefly what are the categories of costs that we have during idle mode periods. What we see is that, well, still more than 50% is related to personnel costs. So, of course, we keep the operation and maintenance team on site even in idle mode periods because the cost of training new operators is much higher than keeping them here. And besides that, they really need to perform this preventive maintenance. So in our case, a minimum of 2 operators is desired. We have more than that just to prepare further operations, but as a minimum, we should have and that's a recommendation, at least 2. Also for safety reasons, of course. Besides that, site management, the time of managers on site, at least 30% during the idle modes, they dedicated only to this preventive maintenance. After personnel, the category that have higher cost is the general maintenances, and here I'm not talking about equipment in specific. I'm talking about a bit of everything. So this includes cleaning of the sites, cleaning of the mirrors of the solar field, for example, cleaning of the offices, site security, and then of course then also some maintenances that we need to contract from third parties, for example. After general maintenances, we have electricity costs here. Nicholas already addressed this, that this is really a topic because these electricity costs are being covered by this project. So, of course, during the idle modes, the idea is to reduce them the maximum as possible. And that's also the reason why the dilution process was the chosen solution for this. But still, with this solution, these are still maybe 14% of the costs. Why? Because, as I said before, these preventive maintenances, from time to time, you will need to activate your heating elements, for example. You will need to turn on your valves, or you will need to perform any task or action that will have consumption. In the last part of the table, it's just a comparison between average consumption between the salt dilution, which was implemented, and what would be the consumption if we just kept the salt molten inside our storage tanks. In this case, we have also a particularity because we don't have right now the possibility of big circulating salts in the solar field because we have there an issue still to be solved. And so if we had chosen to keep the salts inside the tank, we would need to be eating them through the resistances that we have installed there. And so this is it for the preventive maintenance. So passing now for corrective maintenance. Also by definition, corrective maintenance are all the tests that you will be doing to deal with any faulty equipment. And obviously you will maybe most likely found it during operation periods. This table that you can see on the screen is a resume of the situation that we already had along the time since 2021 when we first started operations. So these problems happen both with Yara and solar salts, with the particularity that with the solar salts, the situations with, for example, salt plugs or solidifications are much more critical due to the fact that we have a higher melting point. But starting to address briefly, so we already saw salt leakages. None of it was really, really critical, but still we had it, and in different locations and for different reasons. Obviously, we can expect to have leakages through flanges, for example, and then in that case, it's just a matter of adjusting bolts. But for example, we also had it in reapers, which are also critical equipment that we have in the solar field. And that happened, for example, due to the bad insulation between reapers and metallic support. So in the end, the issue was more related to the design or construction than really regarding the technology of the salts. Regarding salt solidification, we also had it in the HCEs, in valves, in segment of pipes, again, due to different reasons. Sometimes it was, for example, in the reapers, it already happened that the slope of the reapers was not really correct, and so it was not allowing the solar field to drain. Our solar field is drained by gravity, so due to that, it have a drainage inclination. And if its flexible elements do not have the correct slope, of course, they will not be drainable. And this may also cause plugs in the solar field. In segments of pipes, we also already had it. For example, one of our situations was, again, a construction or a design error. One segment connecting to our drainage tank was not really it traced, and due to that, we have, well, kind of a major issue as well. And then the improvements or the corrective actions quite often are, okay, we need to replace this, or we need to put more heat tracing because it does not have it. We need to correct the slope of the pipe or the slope of the reaper. So I can say that we could more or less 100% of the times solve the situations. NOx emissions, we already talked. Well, the NOx formation, it's not possible really to avoid. The NOx emissions, we know we already have identified exactly when they happen. It's just when we open our components, chimneys, flanges, whatever. And so for that, we already have specific safety procedures to avoid warmed operators and even to minimize emissions to the environment as well. Molten salt pump not working to different reasons. We also face that some few times, and short circuit in the valve bonnets fittings. Actually, this was a problem that we had in 100% of our valves. So in the end, yeah, the conclusion is that this is a design error. They are closed-circuit valves. Keeping now to this slide, I wanted not to shock you, but to illustrate a bit the problems that we had. Of course, I did not cover all of them in the table. I just summarized the ones that happened more times, let's say. For example, in the picture on the left, what you can see is a leakage that we had on our feedwater pump, which is this one here. It was not expected. Again, a design error. We are now working in replacing this pump, but at that time, it was really a major issue for us because due to that, we were not able to commission and operate the steam generator. It was leaking. This plunger pump, it was leaking at relatively low pressure. I think it was 20 or 30 bar. It's low for this equipment because it should withstand much more than this. This is also in the center a picture of, it's not an NOx emission, but it is the leakage of the nitric acid that we have. We believe this was the condensation of this NOx and formed this acid nitric here. On the right, maybe it looks a bit shocking. Well, it was the biggest leakage that we had in the end, and it was due to one plug, due to the lack of heat tracing of one pipe on the entrance of the drainage tank, which is this one here. Of course, we needed to analyze what is the root cause. This situation could have been a bit critical actually, because the point was we believed that we had all the solar field drained, and it was not the case. And at that time, we needed to do some maintenance in the pressure sensor in the outlet of the solar field. And whenever the operators just unscrewed the bolts, we had this leakage event. The reason most likely was, well, our solar field is being drained by gravity. Most likely, it's not only one reason, maybe more than one. Incorrect slopes in repair elements, for example, and then draining by gravity. With time, we had this plug here, and so we were not really able to drain the solar field, and it was the reason that why we had that leakage. Of course, we know that the flanges are places by default that you can expect leakages, but not such a thing as you saw in the last picture. Also here, it's a problem that I talked to you about the flow serve valves. Well, this is really a design problem. In the end, what happens is that this heating element is similar to a coil around this part of the valve. The point is that this element was overheating all the time, and so it was then in the end short-circuited, and we needed to replace this. Due to this fact, we also already had problem in one positioner of one molten salt valve because we had a salt plug in the body of the valve. Then someone also tried to activate manually, and in the end, the positioner that should be wrecked, it was completely vented. I'm not sure if the picture really illustrates well, but we needed really to replace this position. Okay, and now I'm getting to the conclusions of what we saw, especially regarding these issues. So most of the occurrences are due to design or construction problems, so they are not really related to the salt itself. For example, these incorrect slopes or bad insulated spots or these short-circuiting heating elements due to bad design. So, and we are working continuously in improving these issues. The only one that I think we did not yet concluded completely was the valve bonnet heating, although DLR made a big effort to try different designs for it. We are still in the path of improving this, but nevertheless, this is a topic more to do closer to the products that they offer to the industry. So heating elements, as I explained, are critical, and implementation of these corrective measures solved almost all of the issues identified, even if sometimes not in the timing that we would like. This is, for example, the case of the feed water pump, because it implied that we need to acquire and that funding to buy another one. And these occurrences also allowed us to improve the training of operators and the procedures that were already established, especially the ones related to the safety. And this is the case, for example, of the NOx emissions. And I think this is it from my side. I thank you again for your attention. And if you have any questions, just let me know.
Thanks very much. I think we had a bit difficulties with the audio quality. I hope you could understand half of it at least. So any questions from the audience or online questions? I think it's nice that you share some real life pictures. I hope some people are still thinking of using molten salt, that they still want to do it. Yeah. Any questions? I think we would then do a small closing session. I asked also Pedro and Eckhard to join because they had another parallel meeting. They will come over. They have a small closing session.